pairs, why do you really have to inflict us this pain of learning a new formalism, and you can't be happy with the usual RNS formalism at level k bigger than 1? And let's try to convince you that this is not an easier problem, but is a more difficult problem. So let's try to answer the question, why are you insisting on taking the level to be 1? So because there are a number of difficulties that arise only when k is bigger than 1. So first, for AdS3 strings with level bigger than 1, if you look at the spectrum at pure NSNS, it contains a continuum of state. So since the boundary contains a continuum, any CFT that should reduce it, so the dual CFT, also contains a continuum, so is not rational. Which in turn means that I can't just work with simple CFT, symmetric orbital of deform. I have to deform it more complicated. Exact CFT2 dual to k different than 1 in AdS3 strings is not a symmetric orbital, but a deformation of it. This was last week, where you have essentially to deform some twist to orbit. Not only can't work with just irrational free theory as a seed, but I also can't have just the symmetric orbitals, but I need a deformation of it. And so far, I haven't turned on any TTbar. So we actually, so this formula is useful to compute some observables, but is not a first principle definition and doesn't allow to compute all of what's in the theory. For example, I don't know how to compute the partition function. So we miss a first principle definition of the CFT2 dual to AdS3 strings. So all these mean it's not wrong to look at TTbar formations in AdS3 CFT2 when the AdS3 does have k equal 1. Not wrong, but it's hard. And it's less hard to learn the hybrid formula, essentially. Yes. essentially two deformations now, this sigma 2 and the TTbar, and it's clear to me if you should do first one, then the other, how, whether they commute or not, how you should do the conformal perturbation theory of each. Yes, but exactly. Okay, I don't know about this dilatant discussion, honestly, but I get that if you deform the symmetric orbital structure, you do not have the instead of each copy, and so you don't know what single trace means. There may be a definition, but I don't know what, at least. Okay, I also don't follow this. It may be right, but I don't know. So let me summarize. So they claiming that AdS3 2 is already difficult enough without any TTbar deformation. So this is a hard problem if you want to add on also the difficulties of deforming it. So instead, we want to look at tensionless string and deform them. So the issue now is that here there is some deformation of the tensionless string, but which deformation? So where should we start? So our starting point, results derived at k bigger than 1, that is having our issue. So is in a paper by Given Itsaki and Kutazov from 17. And what they do, they use the Brown and No worldsheet expression of the asymptotic charges of AdS3, argue what is the worldsheet operator dual to the TTbar operator in the dual CFT. And what they find that this is dual to the J plus, J bar plus, that if you remember in terms of the free field was beta beta bar operator on the worldsheet. Now, this is a result that is in bosonic k bigger than 1. So you may want, is this true also in our k equal 1 theory? What we checked is that, yes, indeed, this, meaning this map, still holds for k equal 1 superstring. I don't know. I don't know. Yeah, I think people, it should be in the literature, the CFT2 perspective. So personally, I don't, but should be known. What I think is known, k equal 1 recover the symmetry of the dual CFT from. So essentially, you should the beta formed Virasoro in a sense from the worksheet. So I don't know what is the algebra that the supersymmetry that is preserved. I think there are papers on that. I don't know the content of, but yes, I agree. I don't know personally, but I think it's known. Yes. Okay, so this means that what we may guess here, so far it's not at all a proof, but a candidate that can replace this question mark is tensionless strings, tensionless k equal 1, AdS3 cross S3 cross T4, deformed by J plus, J bar plus. And in the rest of the I will try to test this proposed candidate. Yes, but I think it depends. Yes, if you write down the asymptotic charges, yes, the L0 is J3. But okay, so I can tell you the way the computation is in k equal 1. So saying that this operator here, so you have the Virasoro algebra on the worksheet, and let me denote curly L's, and you look at this state where this is the start from this state, and this is in, you can write in terms of worksheet variables because we know these L's and we know the CFT2. And this is in a sense the unintegrated operator. Now, since you want it's inside the action, inside here, you would prefer the version that is integrated vertex operator. And this in hybrid formalist variables is dressing this by an algebra on the worksheet, which is the n equal 4, the n equal 4 algebra on the worksheet, which is something like this. And if you do all these OPEs and integrate over the space-time, you find this. So that question we are making and how we make sense of the state. Okay, so how do we test this? We will compute the string partition function and see if we can record in some way square root. So the start is to promote the action of beta gamma, which was this. Beta beta bar term. So this will be the new action. And we want to compute the partition function of the string on locally Euclidean AdS3 geometries with torus boundary. And if I denote by H3 Euclidean AdS3, the global one, then these come in three classes: orbifolds. And if I orbifold by Z, I obtain Euclidean thermal AdS3. If instead I orbifold by Z cross Zm, I obtain the conical singularity. And the third option is that is Z plus Z and corresponds to the cusp geometry. We will concentrate this, since at least on the one that we find easier. I think so far, at least quite manipulations, I think they are. So I don't realize what is wrong. A priori, I want to restrict not to have the problems of having the square root becoming imaginary. But I didn't know, and it was the first time I do this derivation. At this stage, I wouldn't see a problem in having either sign of lambda. And also not a bound. So I'm a bit confused by this. Now, if you do the whole computation, we will cover the root. So, oh, but something went wrong. I don't know where you see this. Maybe. Yes. Probably yes. I would guess so, but I will sketch the step. Probably people in the room will be able to say here. Okay. Now, okay, how is this Z plus Z orbifold act? Essentially, it corresponds to the construction of the boundary torus as a lattice plane. So this means plus Z is generated by two generators that map gamma, that remember is interpreted as the space-time position, to gamma plus T, where T denotes the space-time modular parameter. And T that maps gamma to gamma plus 1. And these equations will become precise enough. What makes this computation doable is that I have free fields. Deformation only affects the beta gamma part. So this means that partition function that on the worksheet that depends on the space-time modular parameter, on the worksheet modular parameter, which I call tau, and on the amount of the deformation. And I have a part that depends on beta gamma, and that will depend on the deformation parameter. And then the rest will go along for the ride, and we can copy essentially the expression of the tensile spring, since this part is not deformed. So if you look in the expression for the tensile spring, this contributes with the Narayan theta function of 4 bosons, and the ghosts cancel the fermion contribution of the T4, so that in total these together give this. Then you have the fermions that give a theta function contribution. And all we have to compute is this contribution here. The rest we can copy from. Yes, so I'm choosing specific space-time spin structure, and I'm choosing the one which is easiest. Also for the other, we'll decorate this theta function. So this beta gamma part. So this will be a sum over all twisted sectors, essentially. So I can write schematically in the notation of orbifolds like this. And I mean is that of a path integral, I have to integrate over gamma, gamma bar, and over the action that I wrote above, with a specific choice of boundary conditions which come from this, and that read so the step, it's a lot here, is to integrate out beta beta bar. So you integrate out beta and beta bar, and what you find is that your action simplifies and takes this form. So we have to compute now the path integral of and gamma bar with this action. So the classical equations of motion with E d bar gamma equals 0 can look for the saddle and schematically write in this form, where A gamma 0 are constant. Then by imposing these two relations, so apply gives is A, and this B. And we can replace action and this. Okay, so I replace action, and what that the partition function has the sum over ABCD, and then the various parts where they come from. Okay, so let me start from the exponential. This is just the action on shell. So a numerator you recognize is B modulus squared, and then you have the volume of the worldsheet torus that gives a factor of tau 2. This explains the exponential. And then you have the one loop determinant, which gives the eta functions. And you still have gamma rho that is unfixed. So you just integrate over the space and use with the volume of the space-time torus, which gives the T2 factor. And the lambda in the denominator, the lambda that was beginning in the action. Yes. So you can also not formulate in terms of. I would say that ABCD run over all integers because they are this z plus z. Yes. Yes, probably yes. Yes, I agree. It's nothing fancy. You can find probably another derivation that is not in terms of path integral, and yeah. Yes, so in a yes, in a sense, this regularizes the delta function that was characteristic of the hexagon tree. So in a couple of lines, we will see. Okay, so what do we need to do with this? We need to assemble the beta gamma contribution with that we know already, integrate over the worldsheet modular parameter. So the string partition function, the one that does no longer depend on tau because we integrate. Takes this form. I'm integrating over the fundamental domain. And I have this, again, this exponential. What you can recognize is that this is the partition function of 4 free bosons and 4 fermions. So this is the T4 partition function. And then if you, okay, so first let's, on the relation with the tensionless string. So you can use the limit representation of the Dirac delta in this expression here that the limit for lambda equals 0 of 1 over exponential of something over lambda is the Dirac delta of that something. To recover the tensile string, what I mean when smoothens the delta function into an exponential, essentially. And then if you massage this, you rewrite the sum over all integers as a sum over modular SL2 transformations and go from the fundamental domain to the upper half plane. So this kind of tricks, and rewrite in a more suggestive form. And I'm define this Z seed. And this Z seed is so this is an integral over the upper half plane. Okay, so at this stage, for experts of symmetric orbifold and TTbar, they should already be happy. But let me say why those that didn't see this formula before. So this is a version of the DMVV formula, digraph Moore, Verlinde, Verlinde, and is the canonical formula that tells you if you know the partition function of some seed theory, I can tell you what is the partition of the symmetric orbit. Here tells us the form of the symmetric orbifold something. And other form here, this other formula here tells us what is the seed in the symmetric orbifold of. And this is the kernel form that relates the partition function of the unformed theory to the partition function of the deformed one. And if you haven't seen this formula before, the way to convince yourself is that you can do the integral. Okay, so you can use some integral representation, or you can just put it on Mathematica. So if you write the undeformed theory as trace of H0 Q bar to the H0 bar, and you do the integral, you find that this gives trace of Q to something, and the something that you find is exactly square root formula. So in summary, this tells us that we have a symmetric orbifold. This tells us that inside the symmetric orbifold, you sit in a spectrum with deformed energies that look like TTbar deformed energy. Yes, sorry, I skipped a step. So from here to here, I'm going to the grand canonical ensemble. So P is a chemical potential counting essentially in the number of strings, the asymptotic winding on the string. So the way you can derive it, I think the way which I find more familiar is that DMVV essentially is telling you you should go to the covering space partition function and sum over all the maps there, okay? and you can derive it in the same way. So the point is that this is a light improvement on the MDV because it calls for non-CFT, right? So the seed here is not a CFT2. So, but you can still define the symmetric orbital because you take many copies, age symmetry, and you can still go to the covering space, and then you have to sum over all maps. And sorry, over all coverings. And the coverings of the torus you can represent as the sublattices of the lattice defined in the torus. And this gives this sum. Yes, papers by Wei Song, if I remember, that they derive it. It look two. Yes. Because I think P left and P right, they are a bit different because we have a different boundary conditions. But this exponential should be analog of Q to the PL, Q bar to the PR. Probably yes. Yes, yeah, I would say so. Yes, yes. In a sense, you can, analogy would say that lambda prime, lambda since sits in the denominator of the, is like alpha prime. Mm, yeah, I don't know how to do the limit. Yeah, don't know this. I can just do the computation and do that at the end and see that I like this Dirac delta representation, but this is interpreted from the beginning and it's not really clear to me at least. Yes, yes. I mean, I agree. In the end, you just have that action. While you would expect a comp of one would be the analogy of PL and P-Rime. Yes, I'm not, yeah. I mean, if you write in the beginning, when I write the beta gamma, there should be introduction of the data. Yeah, I'm not sure. Yes. Yes. No, no, the row is not. So there is an analogy. When I wrote the free field realization, you can compare with the Vakimoto representation of SL2R, which also had a free boson that was describing that for k bigger than 1 described the radial coordinate inside AdS3, but this has gone because it's now fermionized in this p theta. No longer have that interpretation of the radial unit, which in a sense is good because string should be from the boundary. So not have the radial coordinate unit. I mean, this TTbar deformation should drive a flow up. That's how it is interpreted. That's the interpretation. And yes, interpolation. Not that I understand because I don't. A capable one. So I don't have integrate out the metric. And that I don't have any continuum. So usually I associate linear dilaton to a continuum of states. Well, here I won't have any continuum, so I think it should Ramon sector with -1 to the insert. Yes, I mean, okay. I want to pick the easiest one, I agree. But the other spin structures, or instead of 0, 0 here, you have 1/2 or 0, and they work, but they will affect the fermions. So also the fermions will depend on ABCD, and that's why I did that. Yes, but the point is started from AdS3 cross S3 cross. So yes, but I agree that this is the point that did go along right. So if I had different string theory, and it should behave this. But yes, this is formally 0, but you can do the other structures and they make sense. Just a bit more of details, which I wanted to, so that people could follow better. Okay, but here, the place where I cheated. Yes. Interpretation usually, yes. So this because on the worksheet it remains a CFT2. So the CFT2 all after the formation is still a CFT2. So it doesn't. Yes, but here there is no radial direction. So what was the radial direction k bigger than 1 is now fermionized in this p theta, so it's no longer there, this interpretation. So I don't know how to extend the k bigger than 1 interpretation that you have as radial extra coordinate in the bulk as RG flow coordinate in the boundary. I don't know. Okay, I was telling you that I cheated a bit here. So because I was not precise. So here the sum would be over all integers. So you can rewrite as a sum for positive, negative, and zero determinant. Instead, I have just a positive determinant. So I have just thrown out these contributions. Actually, the match work, the EMVV formula. Now, what is the interpretation if I keep all the determinants? So you can, and what you find that negative determinants, if you read this way and do the integral, will change that here this minus becomes a plus. And I mean, if you do the integral is again, this minus becomes a. So this means that the energy of the negative determinant states is as the one of the positive ones plus 1 over lambda. But in the interpretation where lambda is small, this means that the states that correspond to the negative are very heavy, much heavier than the others. And I think that the interpretation is the following, that the determinant of this ABCD is the asymptotic winding of the string. So if I change the sign of the determinant, I'm changing the direction in which the string winds. But the direction in which the string winds is the coupling of the string with the B field. So the usual situation in pure NSNF at k equal 1 is that there are two forces competing. One is the B field, which wants to push the string out. And the other one is the string tension, which wants the string to collapse. And these two balance in such a way that the string can sit anywhere and can sit at the boundary. So these two are usually balanced. But now, if I invert the direction that is induced by the B field, because I change the charge under the B field, then they will no longer compete. So the string will not be tensionless, but it will be very hard to excite. So excitation will give energies which are much higher. That's at least the explanation I try to give myself, since this negative determinant. Might be, yes. So that I don't know. But you see that in the lambda equal to 0 limit, these states are not there because you get a delta function that is not localized on the fundamental domain. So these states are very heavy. So in the undeformed limit, they decouple from the spectrum, you don't see them. But rise with the TTbar deformation, they don't have just large energy with a regularization that is 1 over lambda. And so you can re-see these states above. That's at least what I like, more or less. But then you may try to say, okay, but maybe there's a function of the TTbar formula that also includes the negative and 0 determinants. And I haven't yet checked, but I'm very inspired by the paper by Nathan. And we still have to check, provides a version of, if I understand correctly, of TTbar where you sum over all the terms. I have still to check if all the details is really that, but I would be optimistic that at least we have also a definition of all determinants from the seed theory, from the boundary side. On the worksheet, you mean? So yes, yes. So what I gave components to God's string theory, right? So to construct a string theory should give you first a worldsheet CFT that has central charge 0, but this is not enough. So I should also tell you what is the BRST charge. I should check that to 0, and I should give you some analog of the BGOST, something that I can insert correlation functions, and check that Q with B, something like this, and show that this is indeed can be promoted to a. Yeah, so that guarantees that the deformation is exactly marginal. Okay, but do you know how to write? So, okay, skipping a few steps, I try to step to everyone. So the way the BRST cohomology is formulated here in the undeformed string is that out of the worldsheet, you can construct an n equal to 4 algebra, which is twisted, which means that the supercharges usually have dimension fractional in halves, but since it's twisted, they have dimension 1 and 2, and you take the supercharges that have dimension 1 and you call them your BRST charge. And essentially he's saying that this beta deformation should preserve this structure. So these I don't, okay, it may be, is the 4, which defines the BRST homology in presence of the beta bar written in free field. So I think that's not hopeless. You can reformulate this beta bar deformation interaction as a coset. As a coset, essentially the numerator is your undeformed theory, and you know the n equals to 4 of the undeformed theory. You're taking the coset by some u1s, so it's the exercise of understanding the symmetries of the coset from the symmetries of the numerator that you know with some u1s. So I hope that this can guide in constructing the n equal to 4 also in presence beta. And if you do this, then you have is much better because you're not just counting states, which is what I do now. So first, show that you have a consistent string theory, which I haven't proved. And then you can look at individual vertex operators and see when you have or not unitarity. So for example, when the square root becomes imaginary, you may think that your unitarity maybe breaks down. So if you have the full BRST charge, you can try to see what are your vertex operators, what is their norm, and whether it becomes negative when lambda passes bound that corresponds to negative energies. So that's the dream for the future, if you want. And then, okay, if we have this BRST cohomology, then we have a definition of correlation functions, and we can compute correlators, and is how correlators should be defined in a TTbar deformed CFT2. So thank you very much for the attention. This is all that to say. Ask me questions and teach me something that I didn't understand yet. Thank you very much. Yes, so you may ask the analogous question of what you're asking, I think, is can you redo the same computation starting from thermal AdS, for example? Or yes, or okay, thermal AdS3, I find it easier so far. So there, we are still a bit confused by the details, but what we believe is that, so you see that the orbifold here was the generators of the orbifold, something like the 2it j plus 0 for the cusp, and e to the 2 pi I j plus 0. If you look for thermal AdS, the chemical potential that you insert in the action. So this suggests that you should deform by J3 bar instead of J plus bar. And we find is that if you write the action with the J3 deformation and replace free field interpretation in terms of beta, gamma, and p's of the J3s, you have, and you integrate out the beta bar, you have a mass, but this mass seems coordinates, and it again the same action. And this map is the essentially is the exponential. So this should suggest, so we're seeing how the twisted sectors map the vacuum fermions and how the sphere partition function enters this form. Suggests that if instead you pick thermal AdS3, then you should deform by J3 bar, and in the end you would find the same result. No. Okay. Yes. Well, what? Yes, I know. So essentially, Emily is mentioning he was also discussing is there's AdS3 and then become linear dilaton. These are constructed as functions by currents that contain J3 and K2, right? So yes, should version of series of paper. So one to me, but something like that to be here. You mean that it becomes imaginary? Okay. I don't have an interpretation for that, but would be interesting to look into it. Yes. Yes. All right. Yeah. Yes. Uh, yes, I can't track this way. I agree. Yeah, personally, it's not me. I just have this free field and I go along for the ride. And this plus just comes up with the algebra, and a posteriori I have to explain myself why. And I have this positive determinant as charge. So it's in a posteriori just interpretation. Yes, probably, yeah. Yes. Yes. So Q is e to the 2 pi I t. Yes, because, okay, this does no longer depend on tau. The tau is integrated over. But it's what it should be because tau is the space-time modular parameter. So if CFT, it would be the modular parameter of the. Yeah, maybe calling it a bit misleading, I agree. Yes. So I mean d bar gamma, d gamma bar. Yes. Yes, yes. It's true that the B field is proportional to this, but no, I think the continuum is still there. Um, I don't know, but I think maybe Shuman should comment on this. So the question is, I gave this interpretation of states that you don't see. They become regularized, they're large energy, and they are still in when you deform. And he was asking what's the fate of the continuum part of the spectrum at k bigger than 1, when, for example, you deform by J3 bar. By omega, the asymptotic binding. So yes, it means there is a sign that is as discrete and another sign that is different. Yeah, it's not clear. Yeah. Thank you. Yeah. Okay. I don't know what that means. I mean, it's interesting, but I don't know if it's just the case or I'm AdS CFT framework. So now that you have AdS, sorry, gravity gauge framework, and now you have gravity, I did alone. Yeah. Thank you very much. Thank you.